leader in hematology, oncology, and stem cell research in Jordan and the region. He wrote more than 85 papers in the field of hematology and oncology. He is now a professor of hematology and oncology at Jordan University. He is the director and chairman of the board of directors of the Cell Therapy Center at Jordan University. It's my pleasure to introduce our next speaker, my teacher and the teacher of biological doctors here in Jordan, and hematologist Professor Abdullah Awedi Abbaki. He will talk about the current status of stem cell research in Jordan.
Good morning, ladies and gentlemen. I wasn't quite sure whether to make my talk in Arabic or in English or make a mixture hybrid, so our guests from Edinburgh have a chance to learn some Arabic. Obviously, Arabic language is one of the oldest and one of the most difficult. And as you can see, some of the dots, some of the lines are not originally made for Arabs. They were made for non-Arabs who became Muslims and they needed to learn Arabic. So the skeleton of the Arabic language is very simple. And I'm going to touch upon just some application of stem cells in Jordan, since the field is very wide, since we are doing lots of translational research, which probably can't be covered in the 20 minutes given to me. As perhaps you're aware, the current stem cell technologies are related or focused on several areas in medicine, which are not answered by today medicine, namely to regenerate an organ or tissue, to renew the function of an organ or tissue, to replace an organ or tissue, as well as to rejuvenate organs and tissue. And this is quite obviously linked with the aging process, quite obviously linked with handicaps, both physical as well as mental handicap. And therefore, we in medicine have performed at best limited success in these situations. We really need some new insight into what we can offer and some kind of new solutions to all problems, and hopefully stem cells will be able to offer this. And I'm not going to discuss the issues related to controversies in stem cells. In Jordan, there are several conditions which are currently under the radar for loss of replacement, rejuvenation, regeneration, namely skin diseases, knee cartilage diseases, as well as skin related to long-standing disorders such as diabetes mellitus. But there are also many conditions which are soon will be under the radar, including cardiac, including cornea, as you heard earlier. We are already halfway in that process. We have already generated a cornea in vitro, and we hope to be able to transfer this to a human being within the coming maybe 12 to 15 months. But there are also issues related to our local population. Retinitis pigmentosa, for instance, is a major issue. There are something like 600 kids in the country who are blind because of retinitis pigmentosa. We need to handle this, and we are now looking seriously to use human embryonic stem cells as well as stem cell lines for the management of this work. In addition, we are seriously considering now to introduce gene therapy for these individuals in certain specific mutations which are really important. I think Alzheimer is the coming disease for our population, because until now we have enjoyed reasonably good life, young population. Fortunately, we die early, but down the line, I'm sure we will survive longer. We will still be reaching the 90s, maybe the hundreds. So centenarians will be a fact of life within the coming, perhaps, couple of decades or few decades. So we need to look very carefully at Alzheimer. And currently we have PhD candidates sent abroad for this issue. In my opinion, the methodology or the current status of organ transplantation will transform dramatically by stem cell technology. We will no longer see donor of kidneys, donor of livers, and for that matter, probably even donor of hearts within the coming 20 to 30 years. So organ transplantation is going to be changed dramatically. You probably are all aware that we generated the first epidermal sheet in our world back 2 years ago almost, in May 2012. Our aim was to generate a skin-like replacement. So not only the epidermis, we were aiming to look at the dermis as well. But we succeeded with this one, which was a reasonably easy task, despite the fact that it has not been done by most of our neighbors. Then we thought we would move to another area, which was very important, namely in diabetes, where you have a diabetic foot being a major cause of amputation, as well as morbidity. We thought to try a new product which we have generated in the center, and we call this product an activator. We do not have a patency for this one. We are not big believers in patency because I think we want to produce some products which are good for humanity. And then we tested various concentrations of this product to see whether this would stimulate wound healing. We started with 5%, 10, 15, and 20% of the product. Whatever concentration we used, it was very useful to make keratinocytes migrate and repopulate the area of wound. So we thought we would take this from this experiment to another important experiment. Namely, we generated an epidermis in vitro, and then we injured the epidermis. So this is the injury. So this is the border of the epidermis, another border of the epidermis. This is the injury, simulating an epidermis which is being injured in vivo. And then subsequently, we cultured our active plate with the injured epidermis and see if the epidermis can generate itself or not. And this is the control at 6 hours. As you can see, the wound was still widely open. At 24 hours, it was still widely open. But when we cultured the epidermis in our compound, there was a narrowing of the gap, indicating that there is some good wound healing. And within 24 hours, there was a lot of migration and the wound almost healed. So we took this to the clinic, and currently we are running a double-blind, placebo-controlled trial. I'm just showing you a patient whom we gave him the active plate. This was the baseline. I apologize for the ruler, but this was done early in our experiments. Now we're using a more sophisticated ruler. But this was at the baseline, and then when the patient was injected around, he went obviously debridement. As you can see, the wound started to narrow, and then at 8 weeks, we had a complete healing of that particular wound. We think this is an extremely important compound, and it will see its use in our patients as well as worldwide within the coming perhaps 5 years or so. Then we move to another area, which is now crossing the lines. We no longer, as physicians, work with osteoporosis only, but we also have to take care of our fellow orthopedic surgeons. Being an orthopedic surgeon, you only can, I hope there's no orthopedic surgeon here, you can only sew, you can only put nails and screws and so forth. But we thought we need to have a solution to this, since bone disease is a huge issue, not only in Jordan, but worldwide, with a huge market for this particular product. And you can use a replacement, either autologous replacement, or you can use an allogeneic bone, or you can use synthetic material, or even animal bone for that matter. So we thought we would generate a scaffold in vitro, and then within that scaffold build a bone, and then perhaps return it back to the patient. So we have worked with several scaffolds. I will just expose some of them. Ideally, if you want to have a scaffold, the scaffold has to be biodegradable, it has to be porous, it has to be biocompatible, easy to handle, conductive as well as inductive. It has to be cheap enough to be used on patients. So we work with several scaffolds. We work with the hydroxyapatite scaffold as well as with the additional porcelain scaffold. We use the PLGA, which is the one currently being the most important scaffold we work with. We work with Shatusan, gelatin we did not work with. And we had generated an injectable form of hydroxyapatite as well as additional scaffold, and then we looked at it under the microscope and we could see that our cells put in the proper condition media we generated, they do migrate into pores and spread inside the bone, perhaps making osteoblast as well as osteoclast. So bioceramics for us was an important one. But when we went to a further step, we took the PLGA step. And the PLGA step was reasonably easy. So we took bone marrow samples and then we cultured those on top of the 3D scaffold. And then we looked at signs of activity of osteoblasts. Namely, we looked at alizarin red, bone cosa, as well as alkaline phosphatase. These are present. It means that we do have osteoblasts. We do produce bone as well as bone matrix. So, and then we looked at the cells we were using from various bone marrow samples, and these are the markers we were using. So we had CD73, 90, 105, and this was the gene keeping gene expression, the GPD, gene K plus. It is the gene which keeps the control on cells to make sure that we are getting the right cells. This is obviously our cells at the beginning, and then this is our control. We noticed right from the beginning that when we put these cells in our media, they do produce a bone, a calcium, a mineral deposition. Subsequently, we showed this on alizarin blue, as well as alkaline phosphatase and mucosa staining, indicating that we are dealing with true osteoblasts being expanded in this 3D tissue. Then we looked at the gene which were activated in these osteoblasts, whether really they are the proper genes for bone formation, namely osteocalcin, as you can see, CBFA1, collagen 1, osteox, osteopontin, and so forth. And we found them all in this particular setting, namely K7, 14, 21, and so forth. Then we looked at this in a more microscopic format. So we looked at the sample. Subsequently, after 3 weeks of culture, we found that yes, we had cells which looked like osteoblasts. There was osteoid being formed. And then to our surprise, which was extremely pleasant, that we had also osteoclasts. Remember that osteoclasts were thought not to be present in that particular sample, but they were present. Then subsequently, we looked at it in a more intense manner. So we looked at whether there was actual bone formation in this particular sample, and we could see that yes, the cells at 21 days, they had positive epithelial cell marker, namely CD31, as well as the platelet-derived growth factor was positive, and thrombohydrogen was positive. So in this particular experiment, we proved that yes, we do have our media, which is zero-free, doesn't use animals or any animal product. Does induce the production of bone, osteoblast, osteoid, as well as the vascular problem. So at present, we are now at the second level. We use this on mice. Again, we showed that it works in mice. We have beautiful ossification or formation of bone in mice. Now we are moving to the rabbit. Hopefully within the coming 6 months or so, we will complete our experiment with the rabbits. So if we can prove that yes, this will heal the bone of the rabbit, then the next, since we do not have pigs as experimental animals in Jordan, we will use it on human pigs, and hopefully we will run experiments. We are the closest pigs when it comes to experimentation. So don't get me wrong, I do not mean any offensive wording when I said human legs. The knee cartilage is an extremely important organ tissue which gets taxed in our population. And this is, I think, I don't know if anybody here is above the age of 50. I don't see many of you above the age of 50, but I am above the age of 50. Many of us will have some degree of knee cartilage disorder. Now, the knee cartilage disorder can be classified in various. I put here the simplest, easiest, straightforward X-ray of the knee, and as you can see, narrowing of the space, the formation of cysts, as well as fusion, eventual fusion. So it's grade 1, 2, and 3, and 4. At the beginning, we worked with grade 1 and 2, the simplest, by using, again, a special product, and then subsequently we worked with 2 and 3, and I will show you preliminary results of this. The first experiment, we completed a study of almost 50 individuals, 49 to be more precise, between the age of 20 and 70. They all received our autologous antiplate, which we prepared in the center. They were given 3 injections 2 weeks apart. And we assessed those both from the MRI point of view, as well as using the Canadian score we call cruise score. And in this one, we did not use the normalized ratio, so we used the old gross score. The higher you score, the worse. The lower you score, the better. And we looked at, as you can see, symptoms, pain, mobility, stiffness, all of them improved with a significant statistical improvement, indicating that this particular compound is extremely useful in grade 1 and 2 knee osteoarthrosis in the population study. Then we thought we will look at something a bit more sophisticated, since we do have many people with reasonably advanced osteoarthrosis. So we used the mesenchymal cells, again isolated from autologous and bone. Again, this is showing an MRI as well as the grading I was saying earlier. Again, we have to be very careful. We characterize the cells we are isolating, so we know that we do have mesenchymal cells by showing that they are positive for the markers we require, negative for the markers we do not require, and we have this for every single experiment we do. Now, I'm just showing you real pictures of the first 2 patients. 47-year-old male, he was the first volunteer, and then the second volunteer was a lady, and as you can see, there was considerable improvement in these individuals. This is an MRI picture showing a baseline with a lot of degeneration of the cartilage, and this is showing the post-injection recovery after 2 months, as well as the symptomatology in that particular patient. Similarly, the second patient, again, a lot of edema degeneration. This improved dramatically after 2 months. Then I looked recently at the first 8 patients who completed 6 months follow-up, and I looked at them a little bit differently by doing the normalized ratio of the cruise, reversing. The higher, the better. So if you score 100, that's normal. If you score 0, that's extremely bad. And we had the patients whom we entered had a mean baseline of 54. They all at 6 months improved to a mean of 94 with a significant statistical improvement on these individuals. So within this particular project, these projects were still going. There are several of our scientists who are working on some of those. So I will just briefly review with you what we have. We are currently located in the medical school of the University of Jordan. This was our ex-president inaugurated our site back in 2011. This is the current president viewing our plans and looking at our sites. This is where the site we built. This is how it was. And this is where it is almost now. We will be moving to the center sometime later in the year. We're lucky to have got a grant from the Saudi Fund for Development for 10 million dinars, roughly $14 million, which we are buying the equipment of. This center will be fully leveraged. Large number of people who are working with us. We have more than 36 scientists, part-time, full-time, who are working with us, various the two genders. I don't know if there's a third gender, but currently we have only two genders, males and females, and obviously young kids, future to be. We thought to train them right from now until we reach that particular status. So even in a developing country, when people think that doing research is luxury, I think we have a lot to offer in the area of the field of translation research. I think the stem cells will hopefully be the future to solve many of the unmet needs of our current medical problems. Obviously, we have a major advantage in that Europe and America has been strangulated by their laws. They cannot really have the freedom to investigate and do the research they need on stem cells because of the various ethical and religious reasons. It's fortunate that our scholars in the Muslim religion are very open-minded, and they have allowed us to investigate all these issues, including the use of human embryonic stem cells, including the so-called therapeutic cloning, including nuclear somatic cell transfer. With this, I stop by that.
Thank you, Professor Abdullah, for this nice and comprehensive presentation, and we have time for questions.
Any questions?
Thank you, Dr. Abdullah. Regarding the skin grafting procedure, you will have two patients, one with the regular treatment and one with the stem cell. How much difference between those stem cell transplantation versus the regular without
The current use of epidermal sheet is dominantly in patients with burns, grade 2. Grade 2 burns, instead of using the non-biologic dressing, you can use this as a biologic dressing, and subsequently perhaps you can prevent even scarring, as well as superimposed infections, as well as plasma loss and subsequent life loss. So I think it can be life-saving, especially in grade 2 widespread burns. But obviously we are able to do even more if we can generate another the subdermal layer, dermal layer, which is extremely important, then we will definitely prevent scarring altogether.
Any question? Thank you, Professor Abdullah.
دكتور تنتبهوا علي هون؟ يلا بين الدراسة دكتور معك. يلا